Okay. So, all right. So first of all, I would like to thank the organizers for inviting me to this lovely place, for giving me the opportunity to know members of the Nano Center. I'm quite new here. And I'm going to tell you about something I've recently done together with Yuval Geffen from the Weizmann Institute. And it has to do with interferometers in fractional quantum Hall systems and upstream modes. And this is quite a varied audience, and probably most people, if not all people, do not recognize all the words in the title. So therefore, most of the talk is going to be an introduction, and maybe in the last 5 minutes, I will tell you about the calculations that we have actually done. So the general context of everything is the QuantumHall effect. So let me try to introduce that in 2 slides. So this starts from the classical Hall effect. If we have, this is taken from Wikipedia. If we have, say, a metal and we apply a voltage, we get some current across in the x direction. And if we also have a perpendicular magnetic field, then there is going to be a Lorentz force, that is going to divert the electrons to the side. And this is going to happen until we have enough charge on the side to create an electric field, a transverse electric field that is going to oppose the Lorentz force. And therefore, we are going to get, for a longitudinal current, we are going to get a transverse voltage. So the ratio between them, that's what we call the Hall resistance. And classically, it's just proportional to the magnetic field. But it turned out that's what people discovered something like 30 years ago, is that when you do the same kind of thing in 2-dimensional systems, for example, in semiconducting 2-dimensional electron gas, but more recently people do that in graphene or in oxide interfaces, then if you look here, so this curve is the Hall resistance as function of magnetic field. Let's ignore the other thing. So we see that in general it's linear, but from time to time it's stuck at a plateau where the Hall resistance or the Hall conductance, the inverse of it, is quantized, and the Hall conductance is quantized to a number times E squared over H. So it's basically a pure number times constants of nature, and this quantization, those plateaus that we see here, 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 etc., are so precise that actually they are currently used as part of the standard definition of the electron charge and the Planck constant H. And this number nu can be either an integer, and then we call it the integer quantum Hall effect, or it can be a fraction, and then we call it the fractional quantum Hall effect. So what's the basic physics? Why do we have plateau? Why do we have quantized resistance, quantized macroscopic quantity? So a very rough picture is as follows. In the bulk of the system, if this is the 2-dimensional system and we look from above, then electron trajectories in the magnetic field, they go around in circles. And this circular motion is going to be quantized if we go to low enough temperature. We form what is known as Landau levels. And because those electrons do this circular quantized motion, it turns out that if you apply an electric field, electrons in the bulk, in the middle of the sample, they actually cannot move. The only electrons which can actually move and respond to fields are those near the edge. They correspond to the classical skipping orbits, like that or like that. So quantum mechanically, they become 2 modes, one propagating to the right on one edge of the system and the other propagating to the left on the other edge of the system. So we have perfect channels in which electrons propagate only to one side, each one on a different side of the system. So now if we try to pass current through the system, we are going to have more things moving on the one side than on the other side. And because those sides can be far apart, this is a big sample, there can be no backscattering from side to side. And therefore, we are going to have higher voltage on one side and lower voltage on the other side. But because there is no mixing, this is going to be quantized and not sensitive to the details of the sample. OK, so this is roughly why we have quantized Hall resistance. Another interesting thing that we have in the theory is what is the nature of the elementary excitations of the system. And often in solid-state physics, elementary excitations do not resemble the particles from which the system is built. So for example, if I have a solid and I knock on it, rather than seeing atoms move, I actually excite some kind of waves, which are phonons. And the atoms could be fermions, but the phonons, like photons, are bosons. So what are the elementary excitations of those states? So it turns out that for the integer case, there are basically electrons, but in the fractional case, theory predicts that they are something more complicated. There are entities that are predicted to have fractional charge. This charge, depending on the state, could be 1/3 of the electron charge, 1/5, etc. So it means that when we throw in an electron into this soup, this quantum state, instead of propagating as one bump of the electron charge, it could split into, say, 3 or 5 bumps, which propagate independently. And moreover, there is a prediction that those things, they do not behave like most particles, which are either bosons, where we can have many of them in a single level, or fermions, where we are not allowed to have more than one in a given level. Those things could be anyons, and this means more technically that when we take one around the other, the wave function doesn't return to itself maybe up to a sign, but rather it could return to itself up to an arbitrary phase, or even more complicated things. And there are some theoretical ideas that this could be used maybe even to build a new kind of a quantum computer known as a topological quantum computer. But before we even dream about that, we need to see that those excitations actually exist in the system. So to see that we have excitations with fractional charge, that was actually done already in the 90s. This is one experiment. I will not explain it. This is another experiment, and I will explain that a little bit. So we have our two-dimensional system. We have things propagating here along the edge. We can have here a source. We can apply voltage and inject current, which is going to propagate along the edge. And we have this constriction, which is known as quantum point contact, where we make the edges from the two sides come together. And that there is a finite chance for an excitation going here to either go this way or to tunnel and go to the other side. So there is going to be current going to the other side. And this is happening randomly, so we are going to have noise. And now the situation is similar to, let's say, sitting in the rain under a tin roof. So since the rain is not just a continuous flow of water, it's made of discrete droplets, then we hear noise. We don't just hear some constant sound. In a similar way, in this kind of circuit, we are going to have electrical noise coming from the discreteness of the entities which jump from side to side. And from that, we can extract their charge. So this is what Schottky done 100 years ago with a diode to measure the electron charge. And if you do the same kind of thing here, you see that indeed you have things that propagate and have a charge which is a fraction of the electron charge. So this is okay, this is according to theory. The more challenging thing is to see that those things are neither bosons nor fermions, they are something more complicated. So I told you that when we exchange them, they accumulate some phase. There is some theory prediction. And to see how much phase a quantum mechanical entity accumulates, then we need to build something like an interferometer. This is the way in optics we measure phase. So how do we do that? There are two basic ideas. One of them is the analog of the optical FabryPerot interferometer. So in an optical FabryPerot interferometer, we have light coming to, say, a dielectric slab, and then it can either go through or maybe make this trajectory and then go through, or maybe make a more complicated trajectory, and those trajectories interfere, and we get some interference pattern either for the transmitted or for the reflected light. So the similar thing in our system would be to have two constrictions like the one I introduced before. So now the edges go like that. And now if I have a source here and a drain here, and I send an excitation, it can either go from source to drain this way, or it can go this way. So those two trajectories interfere, and actually it can make several loops around here before it goes out. So now we are going to have interference between the different trajectories. And if we happen to have something stuck in the bulk in the middle, we are going to encircle it and to accumulate a phase which is sensitive to that. And this could tell us about the nature of the elementary excitations. The problem with this kind of setup is that we are sensitive to what is stuck or not stuck here in the middle, and this can fluctuate. And therefore, although there are interesting experiments, the conclusions drawn from them are not so conclusive. So people had the idea that maybe we should build something else. And this is the analog of the optical Mach-Zehnder interferometer. So in optics, we have a source. We have a beam splitter. So we have light going here and here, reflected through mirrors, combined here, and then maybe going to the detector. And the difference between Mach-Zehnder and FabryPerot is that here we can only have two trajectories. There can be no multiple loops. So to have a similar thing in the QuantumHall regime, then we need to build an island in the middle. And then to go from source to drain, we can either do this thing that I showed, or we can have this trajectory. But because we have a drain here, we cannot make multiple loops. So this is like Mach-Zehnder. And now if we think about it, once we send the first, we have two trajectories. We are going to have interference. Once we send the first quasi-particle, then it will do either this way or that way and get here. But this thing is only a fraction of an electron. It cannot go out into the outside world. In the outside world, only electrons live. So it has to wait there. And then the next particle which comes either goes here or goes here. It encircles the first and joins it. Sorry. And then the next one encircles the two. And say if we are in the 1/3 case, then when we have three of them, we have one electron, and now they can leave the system. So actually, even without having anything happening in the bulk of the system, we are going to have quasi-particles encircling each other. And from measuring the interference signal, we can indeed see if there are things that are not bosons and not fermions. So people went to do the experiments. And actually, David Spensak, that we all know, was actually doing that during his PhD. So this is the device. The challenge here is that to create this central island and to bring electricity to it, we need to build some kind of a bridge. And this is not easy, but this was done. And now, to see interference, we need to play with the phase. So we can either use a gate here to change the length of the trajectory, or we can play with the magnetic field and use the Aharonov-Bohm effect. And then people indeed see that as we change the magnetic field, or we change the gate voltage on this electrode, we see the current oscillating. This is a color map, and this is a cut through this map. We see nice oscillations, nice interference, and the ratio between the amplitude of the oscillations and the average can reach almost 1, so we can have almost perfect destructive interference between electrons. But all this is happening in the integer QuantumHall regime, which is nice and interesting, but not enough. When we take the same device, change the magnetic field, and go into the fractional regime, it turns out that nothing is observed. And although they're working for now 10 years to improve and they have very high sensitivity, they see nothing. So we are asking the question, well, OK, what is happening in the fractional regime? Why don't they see any interference? And to understand that, I need to tell you about some other recent observation, which on first look looks unrelated, but we think is actually related. And this has to do with the following. So I told you before that we have no transport in the bulk of those systems, but we have things propagating along the edge in the direction set by the skipping orbits because of the magnetic field. So for example, in simple states like the 1/3 state, we will have just one mode going here and one mode going here. And this is simple, and this gives us the quantized Hall conductance. Everything is fine. But now when we go to more complicated states, like filling 2/3, things get more complicated. So in the 2/3 case, we can understand that as having a state of nu equals to 1, and on top of it, a state of nu equals 1/3 of Hall's. And the end result of that is that we are going to expect to have two modes, one going to the right or downstream along here, and the other one going upstream in the opposite of the expected direction. And naively, if we have modes going in both ways, we would not expect to have the Hall conductance quantized. And this disturbed people at the time. Also, there are experiments which were trying to see charge propagating in the wrong direction, and they failed. And basically, what people realized is that if you insert disorder into the system, what happens, without going into mathematical details, is that two new modes are going to be formed from the original mode. One of them, which I denote by rho, is the one that is going to carry the charge, and this is propagating in the expected direction. This carries charge, just gives us the quantized Hall conductance and everything. And in addition, there is going to be a neutral mode. It's a combination of, say, an electron propagating here and a Hall propagating here, so it's overall a neutral thing, which propagates in the wrong direction. So no charge is carried in the wrong direction, but in principle, there is energy or a heat current which can be carried in the wrong direction. So this is, again, theory, and experiments were planned to actually try to measure and see that. And most of them were done at Weizmann. What they did was the following. So it's the same kind of setup that we have seen before. And now what happens is that we have a source here. The magnetic field direction is such that charge is propagating from here to here. So if we apply voltage here, no charge propagates here. There is no current. But now if we add another source and send current this way, so I told you before that when we send current here, there's going to be noise because it is split. And we see that when we turn on this one, although it contributes no current, it increases the noise of this thing. And this is an evidence that there is something propagating here that we excite that carries no charge but carries some energy and therefore creates some noise. And indeed, if we go to the integer regime where we expect nothing like that to happen, we see nothing propagating in the wrong direction. So this is an indication that whatever they see is not just an artifact of the measurement. And if we go to states where we expect neutral things to propagate in the wrong direction, we do see them in the noise. And interestingly, in fractional states, which are not the ones where you expect to have those upstream modes, they still see some weak evidence of them. So this is a surprise. You can build models that can account for that. But what I'm going to do is something a bit different. What we realized is that we have two confusing observations. On the one hand, we see that in all fractional quantum Hall states, we see modes propagating in the opposite direction, in the upstream direction. And on the other hand, we see that in all fractional quantum Hall states, we do not see interference in the Mach-Zehnder interferometer. So we are telling ourselves, could it be that those two observations are related? Could it be that those upstream modes are the things that suppress interference? So for that, we need to do a calculation. And again, I'm going to skip the details, but just tell you the upshot. The physical idea is very simple. So the thing is that, well, while a charge propagates in this way, in this case, and neutral things propagate in the other way, the things that tunnel here are the elementary excitations, which have charge 1/3, in this case, of 2/3. I'll stick to that. And those are composed from both the charged and the neutral excitation. So whenever charge tunnels from one side, to the other, we are going to excite neutral excitations. So what is that going to do to us? Well, it's going to do the following. So first of all, this is the system. And just to make the pictures more convenient, I'm going to redraw it. So first of all, we are just interested in what is happening here. Sorry, this side is not interesting. And actually, we can, by basically cutting and pasting here, we can reformulate the interferometer in this fashion, where we have modes going this way and this way here and here. And OK, so this purple trajectory is going to be mapped to this purple trajectory, and this green trajectory is going to be mapped to this green trajectory. So it's basically redrawing the same system in a slightly different way, and those trajectories have different lengths, so I account for that here. So this is just a different way of drawing the system. And now to the physics. So if I don't have anything going upstream, so I send in an excitation. It can either do this trajectory or do that trajectory. I'm going to have interference. In order to have interference, we need to have coherence. It means that the time difference between excitation arriving in the two ways needs to be smaller than the coherence time of the system. And this time difference is just the difference in the length divided by the velocity of the excitation. So for example, if we make the length equal, then actually this time is going to be 0, and we are going to have coherence no matter how good or bad our source is to some approximation. But what happens when we have the neutral stuff? Then if we go in the first trajectory, we are going to create neutral excitations there, and they are going to propagate backwards. If we are tunneling here, we are going to create them at the other constriction, and they are propagating backwards. And in order to have coherence, we need to have coherence not just between the charge excitations, but also between those neutral things that we create. And for them, the time difference is the time it takes the charge to go this way, and the time it takes the neutral excitation to go back here or to go back here. So it depends on the sum of the length of the two arms, not just on the difference. So even if we make the two lengths equal, which is what they try to do in the experiment, this could be quite sizable, and this could limit the coherence. And why does this limit the coherence? Because we don't have a monochromatic source. We have a source with a spread of energies. We basically apply a voltage here with respect to here. So at 0 temperature, we have excitations coming in a window of energies of the size of the voltage. So that translates in terms of interference to some oscillations and some decay. But if we are at finite temperature, then our window is smooth. And then we are going to have, when we Fourier transform, we are going to have an exponential decay with temperature and with time. And now if we try to plug in numbers, so for charge excitations, the velocity can be estimated from different experiments. And for a typical size of interferometer of a few microns and a typical velocity, we see that to see coherence, we need temperatures smaller than 25 millikelvin, which is fine. This is what we can get in a dilution refrigerator. But on the other hand, once we have the neutral excitations, since they are neutral, there is going to be less stiffness. It's like sound velocity in a gas versus sound velocity in a solid. They are going to be much slower, and therefore for them, the restriction of temperature could be much smaller, and it could well be below 10 millikelvin, which is below what people can do in the lab. And this could well be the reason why they do not see interference. So now we can do that quantitative and plot different things, and we can think about different geometries to test our ideas, but maybe let me skip that and go to the conclusions. So what I told you basically is that experiments in the fractional quantum Hall regime fail to detect any interference in the Mach-Zehnder geometry. On the other hand, they found upstream propagating neutral modes in basically all fractional quantum Hall states. And what we calculated is that basically those things could be well related, that those upstream modes have a very bad effect on interference, and they could well be the reason why we don't see interference. And if our theory is right, it also gives us a limit on how low must be the temperature and the voltage that we apply for a given sample size in order to see interference. So this is the end, and I would like to thank you for your attention.